So this is what we did last time. So we're going to go through 4, 12, 8. So for 4, if we say the memory address is 8-bit, now this is one word block, then lower 2 bits should be offset, and then the next 3 bits is for index. Therefore, it's going to go 0, 0, 1, and then memory location of the memory 4, memory 5, memory 6, memory address 7. Bring buddies because we need to bring from main memory to cache as a whole block. And then for 12, we have 0, 0, 0, 0, 1, 1, 0, 0, lower 2 bit again as an offset. And next 3 bits, 0, 1, 1 as our index for this memory address 12. And I need to bring my buddies, and this is going to be the tag. And 8, we have 0, 1, 0 as index, and my location is here 8, and I bring my buddies. So that's what happened. After that, it's going to be hit, 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 all the hit. So miss rate is 3 out of 15. Yeah, no, for these scenarios, because it's the lower numbers, we'll work on it. Tag is something else. But basically, the leftover, after we assign the offset and then index, the rest is going to be the tag. Next, we're going to work on 4 and 24. So in this case, it's 100% because 4 is going to be here. And then 24 is going to replace 4. Next time when you call the 4, again in the same location, so we have to replace, replace, replace. Therefore, miss rate is going to be 100%. So this is the case 4. This is 0, 0, 1 as an index. That is right there. And then 0, 0, 0 is going to be the tag. However, for 24, it's 0, 0, 1 as a tag, and 0, 0, 1 as index. So we're going to replace this guy. And then next time when we go call 4, we have to replace 24. Next time we call 24, replace 4. We keep doing it. That's why it's 100% miss rate. Make sense? So let's do this. 1, 25, 34, 15, 24, and 12. 1 in the binary number is going to be 0, 0, 0, 0, 0, 0, 0, 1. It's the first time it's going to be missed. Again, the data size or the block size is a one word. Data size equals the block size equals one word you will be given. Since the block size is one word, how many bytes? 4 bytes. Okay. Therefore, we need to have a 2 digits of the binary number dedicated to which byte. So now, this is 1. So we're going to put it into 0, 0, 0, where the byte location is a 0, 1. So we're going to have, I need to bring my body as a 0, 2, and 3. We call memory address 1, and I need to bring my buddies at this time M0, M2, and M3. So this offset 0, 1, will give us the exact byte location, and we are using big endian. If it doesn't say anything, by default we are using big endians. Therefore 0, 1, 2, 3. So that's the whole block we need to bring to cache. Next, 25. 25 is 0, 0, 0, 1, 1, 0, 0, 1. Again, lower 2 bit offset. Next 3 bits, 1, 1, 0. It's going to be 1, 1, 0 right here. And the byte location is a 0, 1. So I need to bring my buddies what? 24, 25, 26, 27. That's what we need to do. And we still miss. And then the valid bit now is 1 and 1. 34. And 34 in binary number is 0, 0, 1, 0. 0, 0, 1, 0. So this time we need to place up. This index value is 0, 0, 0. So we need to replace this guy, the first one. And then tag value is 001 right there, and my byte address is 10. The third one, so it's 34. So 32, 33, and 35 are my buddies. For your quiz and exam, don't erase this guy, just scratch out, and then you need to re-enter the new data, okay, underneath. Yeah, you need to keep track of hit and misses as well. I'll have another column and say hit or miss. Next, 15 is 0000111. Again, this is miss. And the index value is 011. So we need to put it in this block. And my byte location is 11, which is the last one. So my buddies this time is 12, 13, 14. 12, 13, 14, and 15. Need to bring them all here. And it's going to be 000 as a tag. And when we call 24, it's a hit because 24 is 0001100. So the index, the block location is 110, and we had that when we brought 25, we brought 24 as well. So this time is a hit, and 12 is also hit because we had it 12 here. Yeah, right. So you can just put H or hit. We had this guy hit, this guy hit. So if I put one more column in here, you can put H here and H here. That's all you need to do. First time miss, you need to put actually the miss first, but scratch out and hit. That's what you need to do. We have 1, 2, 3, 4, 5, 6, and hit rate is 2 out of 6. Okay. Yeah, this is the sequence that we're gonna call it. Okay, so again, if you don't mix them up, okay, this is the sequence that we go, but based on the actual code. We're going to execute this and then this. That's the sequence that I put it in. So you cannot execute this guy before this guy. That's impossible. Yeah, if I had another 26 here, that's also hit. So that's the result of this executing 6 LDR instructions in that order. The cache content is going to be this. So we talked about direct map up to this point, and we'll talk about n-way set associative cache. So this is kind of showing two-way set associative way. There is a way 0, way 1. So basically we have 2 blocks in a two-way set associative. So for example, when we execute this guy in the direct map is 100%. However, since we have the 2 ways, we can place those 2 into way 0 first and then way 1. That way we don't have to have 100% misses. But the drawback for this design is much wider cache size. We'll do more a little bit later. Okay, and then fully associative. So this is two-way set associative. So there's a 2-way. And if we have a 3-way set associative, then we're going to have way 0, way 1, and way 2. We're going to go up to 3-way. And then there's a fully associative. So it's just one block wide way. In this case, you just need to fill up the blocks as you go on. So it's much faster to store. However, it's really hard to retrieve because there's no exact location or mechanism or logic to store any of those. We're going to look at the byte address, word address. So up to this point, everything we had, except for the first example, at that time, you guys didn't even realize that's the word addressing or byte address. We just put that in. But now, ARM architecture, we use byte address, but some other architecture, we use word address as well. So let's take a look at the byte address versus the word address. So now, make sure you write in the table, say byte address Okay. With the direct map, so we're going to go through this. So byte address. Now we have 0, 8, 2, 33, 10, and 0. So I'm going to put in the binary numbers for 0, 8, 2, 33, 10, and 0. Since this is the byte address, again, the data, we have to have a 4 bytes. And since there are 8 blocks, we need 3 bits for index. That means we're going to use lower 2 bits as an offset. We're good. Been doing this many times. You should be comfortable with this 8 blocks. Therefore, the index for 0 is 0, 0, 0. And then the tag is going to be the rest. So I put the color coded. So 0, 0 index. This is little endian. That means 0, 1, 2, and 3. Bring my buddies. Now for 8, the index is 0, 1, 0. And then valid bit 1, tag is 0, 0, 0. And I need to bring my buddies. 8, 9, 10, and 11 is going to go there. For 2, that's hit. When we brought 0, we also brought 2. Therefore, it's a hit. And 33 is 0, 0, 1, 0, 0, 0, 0, 1. And the byte address location is a 0, 1. Index is 0, 0, 0. So we need to replace this guy. And bring my buddies 32, 33, 34, 35. Yeah, all right. Yeah, you can just use M3, M2, M1, acceptable. So the reason that I put B in here is a byte addressing. Then we're going to look at the word addressing later. This B, I did it intentionally because we are comparing byte address versus word address. But for you in the quiz, you can just put M3, M2, M1, M0. That's fine. And then you'll be given little endian. If you are not given, you can just assume that that's the big endian. Right. If it is a little endian, I'll say it. If it's a big endian, I'm not going to say it. This is 0, this is 8, and then 2. Even though we didn't call it in here before, but when we call 0, we brought my buddies 1, 2, and 3. That's why it's a hit, because it's already in the cache. And for 33, we have to replace the index 0, 0, 0, because they do share same index values. And then 10 is going to be hit, because we brought 10 when we brought 8. And then finally for 0, again, that's miss, and we need to replace this here. Question about the tag. Tag is, we're going to reserve the lowest part as offset first, and then next number of bits is going to be index, and that depends on the number of blocks. In this example, we have 8 blocks, therefore we need only 3 bits for the index, so that's why we have 3 bits for the index, and then tag is the rest. So this is 0, 0, 0, okay. And this is 0, 0, 0 again, 8. This is 0, 0, 0 again, but however, the larger number, 33, we have 0, 0, 1, 0, 0, 0, 0, 1. That's when you put 33 into binary number, now we have some ones in the upper bit, that's why. So tag value is not automatically 0, because we've been practicing with the lower numbers, that's why it looks like always 0, but it's not. Okay, definitely I'll give you larger number. Yeah. So for buddies, 1, 0, 1, 0, 0, 1, 0, 1. So in this case, let's say memory address OX A5. Then this is A5. And 8 blocks again. Therefore, this guy gonna be offset. When you look at the offset is going to be one of these 4, 0, 0, 0, 1, 1, 0, 1, 1. Obviously, we are using binary numbers. And this will give us exact location of this guy in the byte addressing. So this is 0, 1. Therefore, the big Indian case 00011011. I mean, in the quiz, if you want to just write down 00011011 on top of the block so that you can see where exact location. 01, right here. So this guy MA5 is going to be here. And my buddies, this guy and this guy and this guy. So one less, MA4, and then MA6, MA7. So how you determine your buddies? So you need to figure out exact location offset first, and then this index value in this case is 001. So 001 is the index, and then tag is going to be, in this case, this is our tag value. Now, it's a word address. In the word address, we don't have to put it in the byte in a box. This is one word. So that means we don't need offset anymore. Make sense? We don't need offset. Therefore, it's an 8-block, one-word block, word addressing. Therefore, lower 3 bits is going to be the index, and the rest is going to be the tag. So when we call 0, it's going to be memory word OX0 right there. That's it. It's a word addressing. Therefore, only one word. And then 8, because of the index value is 000 again, we have to replace 0, miss. And then 2, it's going to be right there, 2. And then 21 is right there. 001 is an index. And then A is the same place. We have to replace it, still miss. And then finally 0, let's replace, it's a miss again. So when we say word addressing, you just need to look at lower bits for the index values. Good question. So the question is, when we calculate total size of the memory, we do, when we calculate text size, we said 32 minus n plus m plus 2. And if we are using word, what's going to change in here? This m is the total number of words in a block, so still valid. So in this case, if I say there are 2 words in a block, then we still dedicate 1 bit for the offset. Make sense? So this m will still need it because the size of the block. However, this 2 is from the byte addressing. So if you are using word addressing, this guy is going to be 0. However, still we need this m, because if I say 4 words in a block, then you need to dedicate 2 bits for the offset. We good? Now we're going to go through these 3 different ones, but this time we're going to use word addressing. 8-block cache, and then it's a word addressing. I'm going to go through direct map, 2-way set associative, and the fully associative. And one-way is actually a direct map. One-way set associative is direct map. It's another word, is a direct map. Let's take a look at this. Okay, so let's go through that. So the 0, 0, 0, 0, 0, 0, 0, 0, 0, so lower 3 bit is going to be our index. So the mem 0, 0 right there. And then mem 8, 0, 0, 0, 0, 1, that's the tag. And then lower 3 bits, again, it's an index. So we're going to replace this 0, 0, so still miss. Mem 2, 0, 1, 0 is the index, and the tag value is all 0. It's going to be right there. And then 20 is also indexed as a 0, 0, 0. So we're going to replace very bottom. And then 6, 1, 1, 0 is the lowest 3 bits. That's the index. So memory 6 is right there. And then finally the 8, again, the index is 0, 0, 0. It's going to be there. This is direct map one-way set associative. In here, index is in the vertical way. Also, what we can do, we can put index in the horizontal way. And then we're going to have block addresses going from left to the right. That's the time sequence. We are executing this guy, this guy, this guy, and so on. But in the vertical way, we are executing this guy, this guy, this guy, this guy, this guy, this guy. So I just kind of switch this table, rotate it to this. And also, the total number of sets what we need is the total number of blocks divided by whatever the number in here. So in this case, 8 blocks, total number of blocks is 8. And then we say one-way associative divided by 1. So we need 8 different sets, set 0 to 7. And for 0, is a misses right there. 8 is a misses right there. 2 is a set 2. 20, this is the hex 20. So it's right there because the lower 3 bits is 0. And 0, 6, lower 3 bit is a 6. 8, it's going to be 0. Final cache contents. Now, in this way, one of the benefit with doing this is just by reading from bottom up, that's the final cache in the cache content. In this cache, we have 08, 02, 06, and the rest empty. Now, two-way set associative. So total number of set is the block divided by associative. So this time, 8 divided by 2, which is 4. Copy this down. Total number of sets equals the number of blocks divided by associative. Make sure you copy this down, and you need that for your final exam. How many bits for index in this example? 8 blocks with the 8 blocks in the one-way set associative. How many bits for index? 3 bits. To cover 0 to 7, so cover 0 to 7, that's the 3 bits of index we need to have. Since there is no offset, so 3 bit is going to be the very bottom, the last 3 bits for the index. Now for two-way set associative, how many bits for index at this time? 2 bits, because we have only set 0 to set 3, 0, 0, 0, 1, 1, 0, 1, 1. Therefore, lower 2 bit is going to tell us which is set. So which is set? Set 0, 0. And then it's not like an offset, the byte addressing. Bring as a block, it's not in here. So we just need to put way 0 first. And then next time when we have 0, 0 again, just like 8, it's going to go set 0, 0. However, we fill up way 0. Therefore, we're going to put way 1. The next one is 2. And we need to go set 1, 0. Where is the 1, 0? 1, 0. Where we want to put it in? Way 0. Next one is OX20. So it's going to go set 0, 0. Where? LRU, least recently used policy. So it's going to be this guy. And then next one is a 6. It's a 1, 0. Since way 1 is available, so we're going to put it there. And the lastly 8, again 0, 0. But this time it's going to be hit. So when that happens, you're going to write MOX08 one more time, and then you're going to indicate that as a hit. And then final cache content, you look at all of this cache content from bottom up. So here is the 2008, empty, empty, 0206, empty, empty. Right, it's going to be wrong place. Recently accessed, this haven't accessed to yet. And also you can just look at it as a way 0 is occupied and way 1 is not, so we can put it. But it's the same thing, right? When you have a hit, because we access this guy, so we need to rewrite it in here. Next time when we have a set 0, 0 again, it's going to go into way 0. Index is this guy. We have 8 blocks divided by 2-way set associative. So 8 divided by 2, which is 4. So we need the 4 sets.